Solapur Municipal Corporation serves drinking water to more than 10 lakh citizens across multiple distribution zones. Yet despite infrastructure expansion and operational efforts, equitable and reliable water distribution remains a challenge. Let us understand what is actually happening on the ground. Elevated and tail-end zones frequently receive low water due to poor pressure management. Leakages and aging pipelines silently causes major water losses. At the same time, distribution remains uneven. Some areas receive excess supply while others struggles for basic water. High pressure in certain zones leads to tank overflows and preventable wastage. Unauthorized consumption further increases non-revenue water and disturbs system balance. Together, these challenges highlights the need of intelligent and real-time monitoring water management system. Solapur currently uses SCADA for monitoring key points in the network, which provides essential real-time operational data. However, its coverage is limited to sensor installed locations and does not extend visibility to non-sensor zones. Monitoring today is largely reactive. Faults are identified after they occur, with no predictive analytics or early anomaly detection. Our system integrates both sensor and non-sensor areas to provide complete zone-level visibility across the network. It applies real-time analytics to detect pressure imbalance, leakages, and irregular patterns instantly. Most importantly, it shifts operations from reactive to predictive, enabling early warnings, forecastings, and proactive decision-making. Before designing the solution, we defined 5 core system objectives: data integration from all zones, challenge detection, water distribution analytics, smart monitoring dashboard, planning and forecasting support. Solapur's water distribution network is divided into 8 operational zones. Each zone is served by dedicated storage tanks and distribution pipelines. However, not all zones are digitally monitored. Therefore, we categorize the city into 2 types of zones: instrumented zones and non-instrumented zones. In instrumented zones, pressure and flow sensors are installed at critical network points. These sensors collect real-time hydraulic data from the field. These sensor data is transmitted through RTU and PLC units to the existing SCADA system. SCADA provides basic monitoring visibility. Now we integrate SCADA data into our software database using secure API calls. This enables structured storage and advanced data processing. This completes data integration for instrumented zones. Now let us address the non-instrumented zones. For zones without sensors, we developed a calibrated hydraulic model using APANET. This model digitally replicates Solapur's water distribution network. The model incorporates static hydraulic parameters such as base demand, pipe length and diameter, pump characteristics, and tank levels. Using these inputs, the system estimates flow and pressure values across the network. The simulated hydraulic outputs are exported as structured CSV files. These estimated pressure and flow values are then integrated into our software database. This ensures data availability even in zones without physical sensors. In summary, our system integrates data from 2 parallel pipelines: real-time sensor data from instrumented zones and simulated hydraulic data from non-instrumented zones. Both streams converge into a centralized software database. Now we move into data validation. Once the data from both instrumented and non-instrumented zones is integrated, we move to validation. First, we validate pressure values using CPHEEO, Urban Water Supply Standards. These standards define acceptable pressure range for elevated, tail-end, and normal zones. Based on this, we classify conditions as normal, low, high, or uneven. Second, we validate the hydraulic model itself. Using APANET, we extract simulated pressure values at a junction where the real sensor data is available. We then compare simulated values with actual sensor readings over the time. Both data sets follow a consistent trend with no significant deviation. This confirms that the model is well calibrated and reliable for estimating pressures in non-instrumented zones. With this validated data, the first objective, data integration from all zones, is successfully achieved. Let us move to the second objective, challenge detection. Detecting challenges is not about observing failures after they occur. Let us now see how our system detects all the challenges across the network. Based on field observations and system analysis, we categorized Solapur's water distribution challenges into 3 major groups: hydraulic imbalance detection, NRW and revenue water loss detection, operational failure detection. Each category addresses specific issues within the distribution network. Let us begin with the hydraulic imbalance detection. One of the most critical challenges is low pressure in tail-end zones. Let us consider Zone 8, identified as a tail-end distribution area. In the APANET hydraulic model, we examined 2 critical pipes. Both the pipes shows a pressure of 3 meters. As per CPHEEO standards, the acceptable range for adequate supply is 7 to 12 meters. A value of 3 meters clearly falls below the minimum threshold. Our system continuously compares both the values against these reference standards. When the pressure drops below the defined limit, it automatically classes the condition as a low pressure event in tail-end zone. This anomaly is instantly transmitted to the dashboard, generating a real-time alert for the early corrective actions. Now let us examine a similar condition in an elevated zone. Low pressure is not limited to tail-end zones. Elevated areas also experience insufficient supply due to height-related pressure loss. Let us consider Zone 2. In the APANET model, this pipe records a pressure of 5 meters. As per CPHEEO standards, this remains below the required threshold. Our system evaluates pressure values. Since this pipe belongs to an elevated region, the corresponding threshold applies. When the value falls below the acceptable limit, it is automatically flagged as low pressure condition in an elevated zone. Then the dashboard instantly generates an alert. Having addressed low pressure detection, now we'll move on to the sudden pressure drops. In zone 3, the pipe will be monitored continuously. The pressure drops from 18 meters to 9 meters within a short period. In the graph, you can clearly see the pressure curve sharply going down. This sudden fall is automatically identified by the system as a pressure drop even. Then the system immediately generates an alert. Uneven water pressure is identified as imbalance condition, which occurs when the pressure within the same zone is inconsistent. Let us examine zone 4. Within this zone, one section records a pressure of 16 meters and another section records 13 meters. While 16 remains within the acceptable limits, but 13 approaches a lower boundary of the range. The system continuously compares pressure values across the nodes within the same zone. When the pressure variation between sub-region exceeds acceptable limits, it identifies the condition as uneven pressure distribution. Now our system gives an alert. The second major category addresses non-revenue water and system losses. Let's start with the leak detection. In zone 6, inlet pressure 15 meter, flow 40 lps. Downstream node pressure 14 meter, flow 29 lps. Now raising the question, where is the missing 11 liters per second? The system performs a flow balance comparison between zone inlet and the aggregate demand. Then the dashboard flags a potential leakage condition. Next we examine burst pipe detection. Consider the zone 2. Initially, the node records a pressure of 20 meters and a flow of 432 liters per second. Following the disturbance, pressure collapses to 4 meters and flow reduces drastically to 95 liters per second. The system detects two simultaneous anomalies, a sudden and severe pressure drop and combined with abnormal flow disturbance. When both conditions occur within a short time interval, the event is classified as a probable pipe burst. Then the dashboard generates a high priority notification. Pipe burst suspected in zone 2. Now let's move to unauthorized consumption. Not all losses are due to physical failures. Some occur due to unauthorized and abnormal condition. In zone 6, focusing on nighttime flow patterns, the normal expected pattern is 8 liters per second, but observed flow increases 19 liters per second. The system performs temporal demand analysis and flags potential unauthorized consumption. Let's move to third category, focuses on operational failure detection, which has equipment and storage related failures. Pump inefficiency detection. Zone 2, primary pump has 25 meter pressure and 60 lps, but observed output is 18 meter pressure and 42 lps. The system compares real-time performance. When the pressure and flow both fail below the expected range, it flags pump inefficiency in the dashboard. Rapid tank depletion detection. In zone 5, the tank level drops 6.5 meters to 3.2 meters within 1 hour instead of expected 5.8 meters. Flow is 15 lps while outflow is 35 lps. The system analyzes inflow-outflow balance and depletion rate. Then the dashboard alerts rapid tank depletion detected in zone 5, risk of supply interruption. Now we move to the third objective, water distribution analytics. A zone overview table provides instant zone level insights, pressure, flow, demand, issues, and recommended actions. Pressure trends highlight imbalance patterns while flow comparison reveal possible leakage or unauthorized consumption. Pump performance and boost pressure analytics support operational efficiency. All issues are consolidated into a real-time alert panel for quick decision making. This creates a unified network-wide analytical framework. With this, the third objective is achieved. We'll move to the fourth objective, Smart Monitoring Dashboard. This is a unified interface integrating the live pressure, flow, analytics, and alerts. Key metrics such as zone status, pump performance, average pressure, and NRW rate are visible at a glance. Real-time trends and highlighted critical alerts enable quick, informed decisions. With integrated monitoring and alert management, the fourth objective is achieved. Let's move to the fifth objective, which is a planning and forecasting. Low pressure risk forecast. Pressure in zone 4 is slowly decreasing during peak hours. In the next 6 hours, pressure may fall to 8 meters, below the safe limit of 12 meters, leading to a possible low supply situation. Tank depletion prediction. More water is going out of the tank than coming in. If this continues, the tank will become empty in about 3 hours and 20 minutes. Pipe burst risk forecast. The pipe is facing frequent pressure ups and downs, creating stress. The system estimates a high risk that the pipe may fail if action is not taken early. Here we have demonstrated a few forecasting scenarios for conceptual understanding. In real implementation, the system can analyze all zones, tanks, and pipelines continuously, generating multiple risk predictions simultaneously. This ensures citywide proactive planning, not just isolated case analysis. Through integrated monitoring, intelligent detection, structured analytics, and predictive forecasting, our system transforms Solapur's water distribution into a data-driven management framework. This is not just a monitoring platform, it is an optimized, scalable solution for equitable and reliable urban water supply.